Okay, chapter 9 is about infinite series and sequences. So on the board here are a couple examples of a couple sequences. Now, sequences is just a list of numbers. When you start adding up that list of numbers, then you get a series. So these are a couple series or sequences, but if we started to add them up, like the sum from I equals 1 to 11 of 2n minus 1, I should probably put an n here, then you're adding things up. That's a series. Eventually, by the time we get done with this chapter, not in this section, we'll be able to recognize not only something like this, but a series like this. Sum from I equals 1 to infinity of negative 1 to the, let's see, be 2i plus 1 times x to the 2n plus 1 over, it should be a 2i plus 1, over 2i, it should be a minus 1. We can do it, start at 0. 2i plus 1 factorial. So a crazy something like that is actually something that you're familiar with. This, Mimi's chuckling here because she recognizes it. Oh, you didn't? You should recognize it. That's the sign of x. So we're going to eventually write a very, very familiar function as an infinite series polynomial. It's amazing that we can do that. That you can replace a transcendental function with this infinitely long polynomial. That's our goal. It's going to take a while to learn to get there. We're going to first start with working with series and sequences. So let's start with problem number 2, which introduces kind of like the general notation for a sequence. They describe a sub n as being generated by this term, negative 2 fifths to the nth power, and they ask you just to list the first 5 terms of this sequence. So that would be a sub 1 would be negative 2 fifths to the first power, or just negative 2 fifths. A sub 2 is similar. We're going to put in a 2 here for n, so it's going to be negative 2 fifths squared, which would be 4 25ths, and so on. So we need 3 more terms. It's just going to be a matter of raising negative 2 fifths to higher and higher powers. Or alternately, you could take this answer times negative 2 fifths times this by negative 2 fifths, etc., and get succeeding terms. A3 would be negative 2 fifths cubed, which would be negative 8 over 125. And just 2 more. A to the 4th, or a sub 4, the 4th term in this sequence would be 16 over 625. And the last one would be negative 32 over 3,125. One consequence of the fact that this is a negative number means that when you raise this to odd powers, you're going to get a negative answer here, and here, and here. So something to keep an eye out for future reference. Let's try one more like this, just plugging in and filling in the formula. You could actually get your calculator to do stuff like this. Want to maybe do that one for the calculator? Sure. I don't think it really benefits us too much to do all this stuff by hand. A sub n in this case is 3n over n plus 4. Now I'm going to make my calculator do all the heavy lifting for me on this one. And let's do it this way. First of all, I'm going to program that function into my calculator at the y equals menu. So hit the y equals key, then I'll hit the alpha key, then the y equals key again, and that'll allow me to input a fraction. The fraction I'm going to choose is going to be 3x. I could use an n, but it's It's convenient right now to use an x. 3x over x plus 4. Alpha key and then the y equals key. And that'll give you that menu. The first option down on that menu is to just input a regular fraction. So just type the number 1 or press enter. Okay, so with this all set, let's go through our table setup. Let's just make sure that our tables are going to read out the way we want them to. So this is a one-time setting. Hit the second key, then the window key. Make sure your independent variable here is set to ask. So go down to that line, cursor over to ask, and press enter. Leave this setting that way for the rest of your life. Should be good enough. Okay. Let's go to our table. Hit the second key, then the graph key, and this will set up a t-table for you. We want to know what happens when n equals 1. Oh, when n equals 1, we get 3/5. Not that we couldn't have done that for ourselves anyway. A1 is 3/5. Let's find the rest of these values. If I put in a 2, well, I get 6 over 6, and my calculator reduced that to 1 for me. So that's fine. A2 is 1. Let's fill in the rest of these. 3, 4, and 5. Now, if you don't have a fancy 84, what you're probably going to get here are decimal values. And that's okay. Just realize that they do reflect back to regular fractions. So the rest of these, first 5 would be A3 is, where is it, 9/7? Yeah, 9/7. A4 is 3/2. And A5 is 5/3. So nothing really outstanding or earth-shattering on that one. But it's just listing the first few terms and getting comfortable with this notation. By the way, even though I didn't really tell you what I was using to generate these things, back up here, these terms in this sequence also reflect the same kind of thing. This is the first term. That's A sub 1. That's A sub 2. A sub 3. A sub 4. A sub 5. Can anyone tell me what A sub 6 would be? I want to get the pattern on that one. 720. Yeah, it'd be 720. All right. But if you didn't get that now, we'll be going over that later. It'll be our nice little wake-up call to you. So,
Can you real quick do that? I mean, where did
which one? This one?
yeah, I mean, when you plug it in.
All right. So one more time, you're going to hit the y equals key, and then let me clear this out. You're going to hit the alpha key, then the y equals key again, and that gives you this menu. Now,
I'm just gonna watch it.
it's all right. When you do that, it gives you a regular fraction, a numerator and denominator. So you can type in 3x. Whoops, where'd it go? 3x over x plus 4. Now, if you don't have a calculator like this and you can't do that, then your alternative is to type in 3x divided by parentheses x plus 4. And I guess the reason I like to show this trick here with the fraction is because sometimes people will type in 3x divided by x plus 4 without parentheses. And that's no good, right? Because what's it going to do? It's going to give me 3, which is really 3x divided by x plus 4. It's just going to be 7 forever. So that's not really good. But let's do the table, and let's see the difference between all three of these things. So if I do the second key, then the graph key, so second and then graph, now I'm going to get a table with everything. Unless you're doing it with that fancy fraction method, then you're going to get the decimal values here, which, okay. And then as predicted, everything here in this column was 7.
And where did you go to set up? You set this up.
Oh, you hit the second key and then the window key. That does your table setup. And what you're doing is that you're telling the calculator, I'm going to pick the values for X, and then you give me the values for Y. That's what the dependent set to auto is. If I change that, if I set that to auto, then it's going to start at 1 and increment by 1 and just give me the table that it wants to give me. So there's that table, which works okay for this one. Sometimes you want to start at someplace different, so maybe we can start at 15 and go up by 3. So you get a lot of flexibility there. But I think the most flexible thing is just to have it do what you want rather than what it wants. So that's why I suggest just setting it to ask. Okay. Let's take a look at problem number 10 and 12. So maybe we can do this kind of simultaneously, especially with our graphing calculators. Let's enter in both the functions for this at the same time. Problem number 10 gives you a sub n is 10n over n plus 1. A sub n is 10n over n plus 1. Problem number 12 is negative 1 to the n divided by n. Let's put both of these into our calculator at the same time and get a t-table for the first first 5 or 6 terms. So let me clear out the functions that I have here and enter in the new ones. By the way, as long as you have an 84, your calculator should be able to do this little fraction trick. If it can't, then you need to update your operating system. And you can do that by going to ti.education.com and working through stuff there. You can also call 800 TI CARES, and they'll help you out. So the functions, let's see, alpha, and then y equals key. It was 10x divided by x plus 1. And then the other one was negative 1 to the n divided by n. So again, I'm going to enter that as a fraction. Negative 1 in parentheses raised this time to the x divided by x. So those are my two expressions. Let's do a table and take a look at what I get. So are we okay here? We've got the expressions entered? All right. Well, I better not start at 0 because that would be a problem over here, right? You can see that pretty quickly. It gives you an error. All right, so let me just go type over that. 1, 2, 3, 4, 5. That should be pretty good. And let's see what's happening to these values. 5 and 20 over 3, 15 over 2, 8, etc. So these seem like they're increasing. These seem like they're bouncing around a little bit. Now what they're asking you to decide in problem 10 and 12 is, well, which graph matches the graph of these sequences? So let me put up the graphs for you. You've got your graphing calculator in front of you, hopefully with these values on it. So here's the graphs. Let's see if we can't figure out which one is which. So there's one like this, one that bounces up and down, one that decreases, and another one that kind of bounces up and down consistently. If I'm trying to figure out which one is number 10, then what's happening to these values? They're increasing. Not only are they increasing, but they're always positive. So if they're always positive, then I'm eliminating these two, because these two bounce up and down along the x-axis. So it has to be A or C. Which one is it? Has to be A, right? Because this is an increasing graph. Notice you're not playing connect the dots here. These are just discrete values. We're only plugging in integer values. That's okay. So 10 goes with A. What about problem 12? Here's the values for problem 12. -1, and then +1/2. -1/3, and then +1/4. Well, at the very least, you should see that these things alternate. We've got two choices amongst graphs that have alternating sequences displayed. Is going to be the top one, B, or the bottom one, D. Got a few answers for B. Why B? Yes, exactly. So with D, it's just always the same thing. It's 1 or -1, 1 or -1. That's it. Whereas this one's going to bounce up and down, but it's also getting smaller. It's also getting closer and closer to 0. So it starts at -1, then 1/2, then -1/4, or -2/5, etc. It's bouncing up and down, but it's getting closer and closer to the x-axis. So eventually, what's going to happen? What value is going to get close to as you move out towards positive infinity? 0. It's getting close to 0. So 0 would be the limit of this graph. Okay, looking good on those.
How can it actually be 0 though?
Well, it'll never actually get to 0, but that's its limit. That's what it's moving towards. So it'll never actually touch the x-axis, but it gets as close as you want to get. All right. So good question. Thanks, Ted. Problem number 14. Problem 14 and 16 ask you to describe the pattern you see in these terms here. So we'll start with problem 14. Let me write that up on the board here for us. So we've got 8, 13, 18, 23, 28, etc. In a pinch, could you tell me what the next term would be? Yeah, 33. All right, so it's pretty straightforward. But what we have to do is we have to find the general term. We have to find the a sub n for this one like we had for the previous handful or so. So that's our a sub 1. This is our a sub 2, a sub 3, a sub 4, a sub 5, etc. So what we want is, what does a sub n equal? Well, it starts out with 8. What am I doing to get from one term to the next? Adding 5. So a sub 1 is 8. A sub 2 is 8 plus 5. A sub 3 is 8 plus 5 plus 5. It's 8 plus 5 twice, right? So it's 8 plus 2 times 5. And let's look at this one more time to see if we can't generalize it. A sub 4 is 8 plus 5 plus 5 plus 5. It's 8 plus 3 5s. Now what I'm looking for, maybe I can start to see a pattern here. In fact, let's just try and make that pattern a little bit more concrete now. Let's apply some Photoshop right here. There we go. And I'll write that as 8 plus 1 times 5. Now you can start to look at our index here and this over here. A sub 2 is 8 plus 1 times 5. A sub 3 is 8 plus 2 times 5. What's the nth term going to be? What's the pattern going to be? Eight plus n minus 1 times 5. This number here is 1 less than this one here. 4 here, 3 here, 3 here, 2 here, etc. So that's our general term. Andrew? Yes, so if you distribute this and then combine like terms, then you get 3 plus 5n. So I guess the reason I like this is because it shows you the first term and also shows you the difference. But they're completely equivalent, so it's just a matter of preference. Nothing says that one is more right than the other. Okay? All right, thanks for that one. Anything else on 14 here? No. Looking good. Let's try problem 16 as promised. So this time we've got a sequence like this: 6, -2, 2/3, and then -2/9. Okay, going to have to work a little bit harder on this one. There is one thing that I want to take care of kind of up front, and that is these signs alternate, right? Not that it's really written, but it starts out positive, then negative, then positive, then negative. So the signs are alternating. So that's one thing that has to be true of our general term. You have to have that alternating pattern. So let's take care of that first. So in taking care of that first, let's see here. We've got two possibilities here. And let me just give this a different name. Let's call it b sub n. I can go -n to the first power, or I should probably use a different variable. Call it maybe c sub n. C sub n would be -1 to the n plus first power. So the question is, well, really, what's the difference in these two things? Well, let's put in a few values for b sub n. B sub n is going to generate this sequence. At n equal 1, I'll have -1 to the first power. So I get -1. At n equal 2, -1 squared is +1. And then so on. At n equal 3, it'll be -1, then +1, and so on. So it's going to alternate, but it's going to start out negative. In contrast, c sub n at n equal 1, I'll get -1 to the 1 plus 1 power is going to be +1, and then -1, and then +1, and -1. So it alternates, but it starts out with a different sign. Which term do I want for this particular sequence? Should I have a b sub n type term or a c sub n type term? C sub n, right? Because this starts out positive, then negative, then positive, then negative. So whatever my general term is, it's going to have something like this. The other part of this is we have to figure out, well, what is the general pattern? Can you see what we're doing to get from one term to the next? Good. Multiply by 1/3. All right, so I multiply by 1/3 once, and then twice, and then 3 times. So playing the same kind of game that I did for the previous one, I'm going to get a sub n. It's going to be -1 to the n plus 1 power times 1/3, not to the n, but to the n minus 1. Now, there's a lot of different equivalent ways you can write this thing. This just happens to be one of them. When I grade papers on this, a lot of times I have to look carefully through at your work and make sure that what you have is equivalent to what I think you should have, and that it generates this sequence. Okay, looking good on that one. Now, earlier I hinted at something, and let me come through with that now. That was a little introduction to some notation that I'm not sure I've really used that much in this class. And it's illustrated like this. 4 with an exclamation point. Oh, Andrew, question?
Should you have a 6 in the front of it?
Yes, I should have a 6 in front of it. Thank you. Yes. So that would be my first term, would be a 6. Yes, thank you. Okay, so let's go back to this notation and understand where you would consider such a thing. So, in the middle row in class, there's 4 people. And a question that I would ask my statistics class is, well, how many different ways can I order the people starting with newer and moving back? Well, in newer seat, I have 4 choices. And for each choice there, I've got 3 more choices for Vicky's seat, times 2 more choices for Dawood's seat, and then Dylan, that's your seat. We got one choice when we get down to that seat. So now, this notation is called a factorial. Fortunately for us, it's got a nice name. We can talk about more about this. If this were an English class, do you know what that would be? 4! But fortunately, it's a math class. All right, I like doing that. I get to wake you guys up a little bit. All right. You're used to this joke. She knows it's coming. All right, so let's play around with the factorial notation a little bit. Let's learn where it is on your calculator, because you can calculate these things. It's a lot easier than doing 4 times 3 times 3. There's a button for that. So let's do 10 factorial, which is an enormously big number. So if you had the 9 players on a baseball team plus the coach lining up to hopefully not kneel at the national anthem, but lining up for the national anthem from some fashion, how many ways could you arrange them? So you hit the 10, then hit the math key, go over to probability. So that's the fourth menu across the top. Does there look like there's anything promising in here? 4th option down. So 10 factorial should be over 3 million, which is a staggeringly large number for such a small thing like 10. You can have a little bit of fun with the factorial notation. For instance, if you wanted to figure out how many ways there are to pull 5 cards off the top of a standard deck, say you're playing poker, that'd be 52 factorial divided by 5 factorial times 47 factorial. And that number, if you took the time to calculate it, would be about 2.6 million different hands that you can get. So if you get dealt a royal flush, that's pretty good. There's only 4 of them out of those 2.6 million.
Why are they pulling 5 and 47?
Well, there's 5 card poker hand.
All 5.
Yeah. All right. I would love to go into that more. That's actually a fun part of statistics and probability, but that's a little bit of a digression. So let me try and veer back on track. Let's look at a few terms of the sequence for. Well, actually, let's look back here. I think somebody got this one earlier when I asked what the 7th term was. Somebody said 720. And what's going on here is that the general term, a sub n, is n factorial. So like I said, the next term would be 720. So let's keep that in mind as we look at problem number 50. And we'll try and reverse engineer problem number 50. They give you the first few terms. So those first few terms look like this. 2, 24, 720, and then 40,320. So that's what they give you. Well, hopefully a couple of these look at least a little bit familiar. fact, they should. So let's do this. This is our a sub 1. This is our a sub 2, a sub 3, and a sub 4. That's what those terms are. We need to figure out a sub n. Okay. Let's think here. Well, do you recognize any of these numbers? What's a sub 1 equal to? Somehow or another, that's 2 factorial. What's a sub 2 equal to? 4 factorial. And a sub 3, 6 factorial. Any guesses as to what this is? 8 factorial. So in general, what's the nth term going to look like? A sub n would be what? Perfect. 2n factorial. You can actually check that on your calculator if you wanted to. You could make your calculator grind out all these values. So I could put in that general term here, parentheses, 2x, and then the math key, 2x factorial. Now let's go to the table. And there you go. You're getting all these. Quick little word here. It looks like it doesn't have quite enough room for 10 factorial. But if you cursor over to the right, put your cursor on that, you will see as many digits as your calculator can show you down at the bottom. So there's 10 factorial. Like I said earlier, about 3.6 million. By the way, what do you think the biggest number I can enter here would be? At what point is this going to be too big for my calculator? 15? I think it's a little higher. I'm thinking 34 will work, but 35 won't. 35, error. Yeah. So 70 factorial is too big for your calculator. Basically, it's bigger than a Google. So factorial is a number that grows really big, really fast. Let's take a look at some other terms, some other sequences, and see if we can't simplify some of these. We'll look at 18 and 20 next. So, problem number 18. N factorial over n plus 2 factorial. And the goal here really is to simplify these expressions and to get comfortable with the factorial notation. N factorial in the numerator, I'm going to leave it alone. But in the denominator, I can kind of split that up a little bit. So let's see. That'd be n plus 2 times, what's the next one lower than that? N plus 1. And what's lower than that? N. And let's just stop it at n factorial. Now, why am I stopping it at n factorial? What do you think? What's that? Not really 0, but I think somebody else said it. Fun? Yeah. You can cancel now, right? It's the same in the numerator and denominator. Everything's being multiplied, so you can cancel that. Equivalently, this is 1 over n plus 2 times n plus 1, and we'll leave it like that. All they're looking for is for you to simplify that one there. Let's play that game again with problem number 20. Two n plus 2 factorial divided by 2n factorial. This time, see if you can't simplify it.
said that. The story I heard was that Larry Bell and all his workers were hanging around one night. They had to come up with a new name. In his drunken haze, some guy's like, "They got it. I saw a Shakespeare play last night. We'll call it Oberon." And the name stuck. Okay. Looking good.
So you cannot factor out the 2 here. Instead, what you have to do is kind of pare this down the way we did the last one. So if I subtract 1 from whatever this integer is, the next one down would be 2n plus 1. Subtracting 1 from that, the next one down would be 2n. And I could keep on subtracting, but I've already got a 2n factorial in the denominator. So I'll stop it there so that I can get some cancellation. And these 2 cancel, so I'm just left with 2n plus 2 times 2n plus 1. And that's it. I mean, I'm not sure I'm really interested in you foiling it out or not. Doesn't matter. The important part is you simplified it. Yes, sir. Well, that's what we do when we do a factorial. You multiply it by the next smallest integer. So to get from one integer to the next, in terms of a decreasing manner, you're subtracting 1. All right? Anything else on problem number 18 here? Our eventual goal is to figure out, well, what happens to these series in the long run? Are they tending towards something in particular? In other words, do they have a limit? Do they converge? So let's take a look at problem number 6. I mean, not 6. It's got a 6 in it. Problem number 22. A sub n is 6 plus 2 over n squared. So the question is for you to find the limit if possible. Basically, it's this. Limit as n approaches infinity of 6 plus 2 over n squared. Well, if you wanted to be really methodical about it, you could split that up. Limit as n approaches infinity of 6 plus limit as n approaches infinity of 2 over n squared. That first limit doesn't depend on n at all, does it? It's just a constant. So that part's just a 6. What's this limit going to equal? 0. Do I need to pull out L'Hopital's rule for that one? Could I pull out L'Hopital's rule? No. It's not infinity over infinity or 0 over 0. It's not like that. But it does go to 0, so overall the limit is 6. So that's where these terms are headed. Let's try a different one. Problem number 24. A sub n, in this case, is the cosine of 1 over n. Same question as before. Does this converge? In other words, does it have a limit that I can calculate? Cosine of 1 over n. Now, cosine is a nice, smooth, continuous function. And because of that, Amila, we can interchange these two operations. I can do the cosine of the limit as n approaches infinity of 1 over n. I can get away with that here. What's that limit? Overall, yeah. No, just the limit part, though. And the cosine of 0 is 1. So eventually, this should head to 1. Let's take a look at that graphically. So let's go over to Desmos real quick and look at y equals cosine of, whoops, gotta get rid of the caps lock, y equals cosine of 1 over x. So this stuff in the middle, does it matter to us? Not really, because we're looking for the limit as x approaches infinity. So what we're looking at is what happens to the value of cosine as you get farther and farther out the x-axis. And you can see that it's settling down pretty closely to y equals 1. All right. I can't be clear enough about this. What you see from your t-tables, what you see from your graphs, and what you calculate from your limit all should say the same thing. We're going to do that again for problem coming up. In fact, let's do it for problem number 28. Let's see, 9.1 sequences. There. Okay, so let's enter this one into our graphing calculator and look at it several different ways. So the sequence in problem number 28 is, oops, rats. Here we go. A sub n equals 2 minus 1 over 4 to the nth power. We're going to look at it first with a table, and then we're going to look at it with the graph, and then we're going to calculate it analytically. Kind of like what we did with the last one. Calculate it just directly. Now for the table, let's enter this graph, or this equation I should say, into our graphing calculator. Now I'm not going to get all fancy with this like I did with some of the other ones. I'm just going to enter it in any way that I see convenient. So it's going to be 2 minus 1 divided by 4 raised to the x power. And doing it this way, I'll just get a nice decimal value. That's fine. So let's go to the table, second table, and let's enter in some more values. 6, 7, 8, 9. I think we can kind of see what happens. As I reminded you or told you just a little bit ago, if you want to see more of the y coordinate, you can just put your cursor on the y column. So at 2, we're at 1.9375, then 1.98, 1.99. Are these tending to anything? Is there a pattern in here? Yeah, it's getting closer and closer to 2. In fact, down here at y equals 8, y equals 9, you're so close to 2 that it just literally rounds to exactly 2. Even though we're not at exactly 2, but that's where it rounds. So from our table, we see that we get exactly 2. How about the graph? Well, you could graph these. I've chose to do it here because it's nice and easy. Take a look at what's happening to the graph. Where do these numbers settle down to? 2. Yeah, they definitely settle down to y equals 2. So the graph is again telling us the same thing that everything else is. That our table does. Let's check it analytically. So let's calculate the limit as n approaches infinity of 2 minus 1 over 4 to the n. I'm not going to be as, particular about this one as I was with problem number 22. Let's just take this limit. The limit as n approaches infinity of 2 is 2 What happens as n approaches infinity to 1 over 4 to the n? Goes to 0. So all three of these things agree. You had the graph, you had the table, and you had the analytic calculation. All of them say they go to 3. They should all match. It's a nice double check of your work. There's nothing at all that prevents you on a test from graphing it and looking. It's like, does that match my calculation? It should. That'll make two of us happy that you checked it. You because you get it right, me because I like grading papers where they're all right. So, all right. How are we looking on 28? Okay there? Let's try problem number 40. Y equals n times the sine of 1 over n. Whoops, I put y equals. I should put a sub n. My bad. This is a sequence. Not a, well, I guess it is a function, but we're worried about the sequence, a sub n. Okay. Hard to tell with this one. In fact, I got a little something for you that maybe we'll do between sections that is kind of like an application to this. If we start looking at the limit as n approaches infinity of n times the sine of 1 over n, well, on the one hand, we get infinity. On the other hand, we get the sine of 0. What's the sine of 0? 0. So what wins? Is infinity times 0? Is that 0? Is it infinity? What is it? Well, tell you what. Let's try and take a look at it graphically and see if we can gain some insight from this graphically. So let me shut off this one here. And you could graph this on your graphing calculator. There's nothing wrong with doing that. I just happen to have this already up. So, again, we're not worried about what happens in here because we're looking at the limit as x approaches infinity. Does it look like it settles down to something? Infinity times 0 gives me what? In this case, 1. Looks like it's going to 1, right? Okay. But the problem that we're running into when we look at this is it doesn't look like there's a convenient way to calculate that, to show it analytically. But we kind of know in the back of our minds, it looks like it's going to 1. Infinity times 0. You want to mess with the minds of some of your fellow students that are maybe in a Math 1100, tell them infinity times 0 is 1. Woohoo! All right, that's what we know what it's going to be. But how do we show that? Well, we show that with L'Hopital's rule. But we can't quite use L'Hopital's rule yet. Why not? Yeah, it's not an indeterminate form. Well said. Are there any tricks that we can use? Yeah. Instead of multiplying by n, you could divide by 1 over n. That's an equivalent form. And now you've got 0 over 0. That's what you needed. So that was the little trick in this one. See, and you thought you were done with L'Hopital's rule. All right. So what do we do now? We can use L'Hopital's rule. So I think on the test when I graded it, I saw people treating it as if it's the quotient rule. When you apply L'Hopital's rule, it's the derivative of the numerator divided by the derivative of the denominator. So this will equal the limit, and please carry that limit term around because it's not true unless you have the limit here. The derivative of the denominator is going to be negative 1 over n squared. Right? Because you got n to the negative first, If I do ddn, I get negative n to the negative second, or negative 1 over n squared. So that's what's happening in the denominator. How about in the numerator? In the numerator, the fun has just begun, right? Because you get to use the chain rule. Woohoo! How cool is that? What's the derivative of the outside? Cosine of 1 over n times the derivative of the inside. This is where mathematicians are famous for something like this. From here, the problem's already been shown. Well, we know what the derivative of 1 over n is, so I'm not going to calculate that again. It's just 1 over n squared. And something nice happens here, right? Bada boom, bada bing. Those cancel each other out. Nice. You're just left with the limit as n approaches infinity of cosine of 1 over n. Actually, I don't... Let's see. What's that limit going to be? What am I going to get here? Cosine of 0, which is 1. And we saw that like 5 minutes ago when we looked at the graph. But if I ask you for an actual proof, this is what I need to see. Is there anything wrong, though, with looking at the graph on your graphing calculator? No. Do that. Make sure that your answer matches what you're giving me. It's a freebie. You can check your answer for free. So if you choose to or not, it's up to you, but I think you're foolish if you don't, because you can easily see if you got it right. The one thing you have to be careful about here is if you do take time to check your answer, make sure that your graphing calculator is set to radians. So other than that, it should be good. Write in the y equals key. So let's take a quick look at it on the graphing calculator. The original function, so it's going to be y equals x sine of 1 divided by x. And let me set up my window. Now I'm looking towards n is positive infinity, so maybe I'll start this at 0. I know that the biggest that sine could be is 1. The minimum is negative 1. So I'll go from negative 1 to 1. And let me go a little bit higher than 1.2. I think that should be pretty good. Let's do our graph. There you go. So if they're not convinced here, what you can do is you can hit the trace key right here. That'll put a coordinate on your function. You've got your x and y coordinates. Watch as I increase my values for x. In fact, I'm just typing in 6, 7, 8, and you can see the y values. 9. They're getting closer and closer to 1. So nothing wrong with checking it on your graphing calculator. Thanks for the question. Anything else on number 40 here? Let me introduce one last thing here for us, and that is monotonic sequences. What's a monotone? If somebody's speaking in a monotone, what is it? Yeah, just stays the same. Mono, one, just stays the same. So hopefully your instructor's not monotone, all right? Hopefully I try and keep you a little bit awake, although I do sense the native's getting restless, so I'm going to try and hurry up and finish up this section. But we can talk about a monotonic sequence. Monotonic sequence. And the definition for that is on page 590. So monotonic sequence is going to be a sequence in which the terms are always non-decreasing or non-increasing. Basically, they're going one way or another. So a monotonic sequence could look like this. A sub 1 is less than or equal to a sub 2, is less than or equal to a sub 3, and so on. So basically, it's non-decreasing. In a similar way, you could have a non-increasing sequence. A sub 1 is greater than or equal to a sub 2, is greater than or equal to a sub 3. So the terms are always tending to get smaller or at worst stay the same. So this would be a non-increasing sequence. Now there's some nice things that happen if you have what's called a bounded monotonic sequence. If this is always increasing, but yet there's a bound up above it, that is, it never gets higher than some particular value, then it has to converge. So we've already seen examples like that today. Let's go back to this one right up here. The biggest that this thing would get would be 2. Because these values are getting closer and closer and closer to 2, and because the line y equals 2 is an upper bound, then this thing has to have a limit. It has to eventually converge to 2. So a bounded monotonic sequence is going to converge. Question is, how do you show that something is a monotonic sequence? Let's actually start by showing something that's not a monotonic sequence. That'd be problem number 60. A sub n equals the cosine of n divided by n. Let's just do this one in our calculator. So I'm going to enter that and do it in a table. So let's clear this out. Cosine of x. Make sure you hit the right closing parenthesis and then divide by x. So cosine of x over x. Make sure that you're in radian mode, not degree mode. Calculus is done in radians. If we go to our table, take a look at the values for y. Are they always decreasing? Are they always increasing? Or what's going on? Is it monotonic? No, it's kind of all over the place, right? It's going up, it's going down. It's, kind of like the cosine function itself. It's going to bounce up and down a little bit. I mean, eventually it'll get to 0. It does have a limit, but it's not monotonic because it's not strictly going in one direction. So you can just do that one by example. Not monotonic. Okay, how about problem number 54? In this case, a sub n is 3n over n plus 2. And maybe it wouldn't hurt to look at that one, at least in terms of our tables. So I'm going to plug that one into our table. So 3x over x plus 2. And then let's do our table. And take a look at what's happening to our values. You go 1, 1.5, 1.8, 2, 2 and 1/7, etc., 2 and 3/4. So what's happening is that they're always getting steadily bigger, right? So they're starting to look like a monotonic sequence. How can we show that? Well, we could treat this as a continuous function and show that it's always increasing, at least on the range of 1 to infinity. How could you show that a function is increasing? Who'd you have for Calc 1? Yeah, take its derivative. So let's just call that 3x over x plus 2. If its derivative is greater than 0 on that interval, then the function's always got to be increasing on that interval. So let's see where the derivative is greater than 0. Now, I don't have to worry about -2 because we're dealing with values of n that are positive integers. So n equals -2 is not really going to come into play for us. Parth, what rule do I have to use to differentiate this? Quotient rule. Said with enthusiasm. Thank you. So start with the denominator. You square the denominator, and then the denominator times the derivative of the numerator minus the numerator times the derivative of the denominator. So let's see what we're going to get. That's going to give me 3x plus 6 minus 3x over x plus 2 squared. So it's going to give me 6 over x plus 2 squared. How can I conclude that that's always greater than 0? Yeah. Square is only positive for positive values of x here. And 6 is always positive. So it's always increasing. So it's a monotonic function. And that's a good thing. You can see what happens when we try and graph this thing. Let's take a look at its graph real quick. Let's say goodbye to this one. Y equals 3x over x plus 2. Oops. How about x plus 2? And let's look at the graph of y equals 3. So what's happening is that eventually, as you move out towards x equals infinity, this thing is always increasing, but it can't increase too far. Eventually, it's got to run into this boundary. So the limit of this graph would be 3. And of course, I think you can calculate that analytically pretty quickly. In fact, I mean, it'd be like burning down a house to roast a pig. But if we look back here, could I use L'Hopital's rule to calculate the limit as n approaches infinity of 3n over n plus 2? Technically speaking, can I use L'Hopital's rule to do that? Sure. I mean, it's really pulling out the big guns. It's squirrel hunting with a bazooka, but it works. 3 over 1 is 3. All right. How are we looking on that last example? Let me give you some homework here. For homework, try 1 through 63. This is section 9.1, 1 through 63. And you can skip problem number 41.